This is Unit 4, Topic F. We'll continue to look at integrals, antiderivatives, and the ones we'll look at in this section will involve the natural log function. So I want to start by reminding you of this integral. The integral of 1 over x dx, which could also be written as just dx over x, is the natural log of x plus c. And actually we usually put absolute values here in this natural log, just to make sure we're not putting a negative number inside of a log. All right, as you look at this, keep in mind then that if the denominator was something more, perhaps u could be the denominator, and then we'd end up with a natural log u as our integral. So sometimes the best choice of u is just the denominator. Let's try that out in a couple of examples. In number 1, there's no obvious inner function, so I'm just going to look at this denominator, 3x plus 5, and try to let that be my u. So du dx will be 3. Du is 3 dx, and 1/3 du would equal dx. This entire denominator becomes my u. So I have the integral of 1 over u. And then the dx gets replaced with a 1/3 du. So let's see. That 1/3, we're always pulling that out of the integral anyway. Why don't I just go ahead and do that right now? I'm going to put the 1/3 in front, and then the du. Just cleans it up a little bit. All right, this is exactly the situation we were talking about, right? This is now that integral, just with u's instead of x's. So I'm going to get 1/3 times the natural log of u, or the absolute value of u there. And then the only thing left to do is to plug back in for the u. So I'd have 1/3 the natural log of 3x plus 5 plus c. All right, let's try the second one. Once again, I'm looking at that algebraic fraction, and I don't see anything obvious as an inner function of a composition. So my second choice is just to try to let u be the denominator. X to the 4th plus 8x. The derivative would be 4x cubed plus 8. And I'm going to notice that 4 could get factored out of that. And when I do, that's going to give me the x cubed plus 2 that I've got sitting right there. So let's go ahead and factor out that 4, as well as bringing the dx over. And that means that 1/4 du is equal to x cubed plus 2 dx. All right, my u was this denominator. So we'll put that u in the bottom. And then this entire thing, this x cubed plus 2 dx, all of that can get replaced with the 1/4 du. So kind of like I did in the last one, the 1/4, I know a constant multiplier can just get pulled out of the integral. I'll pull that to the front, and then I have just du. All right, once again, this is the natural log integral. It just happens to be in this form this time. So I would have 1/4 natural log u plus c, or 1/4 natural log of x to the 4th plus 8x plus c. All right, in our next problem, we're going to look at integrating one of the trig functions that we have not yet talked about as an integral or as an antiderivative, specifically the tangent of x. In this form, since tangent of x isn't anything we've talked about so far, at least not on this left-hand side. I know it's over on the right, but that's because we're going to do it now. But nothing we've done so far is the integral of tangent x. I need to look for a way of doing this. One common trig identity to use for tangent is sine x over cosine x. And as soon as I've got a fraction, letting u be the denominator is a possibility. So let's do that. In this case, u would be cosine x. That means that du would be the derivative, du dx would be the derivative of cosine x, negative sine x, and du is negative sine x dx. I can bring the negative over. Minus du is sine x dx. All right, I do have a sine x dx. That's a good thing. So I'm going to go ahead and replace my denominator, that cosine x, with a u. And then I'm also going to replace the sine x dx with a minus du. That minus sign, I can just pull that out in front of the integral. And then the du will go up here on top. And once again, there's that form of the natural log integral. In this case, I've got negative natural log absolute value of u plus c, or negative natural log absolute value of cosine x plus c. That one is one we can use often enough that now that we've figured out where it came from, you'll notice it actually is included on your list. So you can use this one from now on. I will mention that the cotangent integral is done in a very similar way. The secant and cosecant require just a little bit more manipulation, but they all have to do with just letting u be a denominator. So we'll go ahead and say that these are all acceptable now. They're all done in a similar way to the one that we just did. All right, one more example like this. In number 4, I once again see no particularly obvious inner function. I guess maybe the 5x, but I don't think that's going to change things enough to really be helpful. So let's let u be the denominator again, e to the 5x minus 2. So my derivative would be e to the 5x, and I'd have to multiply that by 5 for the chain rule. So du is e to the 5x dx, and 1/5 du is e to the 5x dx. All right, my denominator becomes the u. So u on the bottom. And then this e to the 5x dx together can get replaced with the 1/5 du. I'm going to put the 1/5 in front of the integral, and there's the du. So the hopefully now familiar form of that natural log integral, 1/5 natural log u plus c, or 1/5 times the natural log of e to the 5x minus 2 plus c. So letting u be a denominator is sometimes a good strategy. When you do that, expect a natural log as part of your solution. All right, There's actually a common algebra trick that gets used quite a bit with these integrals, and we'll look at our last couple of examples in this area. The trick is to use long division. When the degree of the numerator of an algebraic fraction is greater than or equal to the degree of the denominator, try doing long division before you try to integrate. Right? So when I look at this problem, the degree on the top is the same as the degree on the bottom. So let's start here by just dividing this out. It is long division since there's two terms, not just one in the denominator. And I'm just going to take 2x divided by x, which would be 2, multiply 2x minus 4, and change the signs. It becomes negative, that becomes positive, and we get a remainder of 3. So I'm going to rewrite my original integral as the quotient 2 plus the remainder would be 3 over x minus 2. I now have a sum of two separate pieces, and I know I can integrate those separately. So this would be the integral of 2 dx plus the integral of 3 over x minus 2 dx. This first one is really straightforward. I'll just get 2x plus this one. If I now let u be the denominator, I should be able to get a natural log integral out of this. So let's try it. U is x minus 2, so du dx is 1, and du is simply equal to dx. My denominator is u. That 3 could actually get pulled out of the integral, and then the dx is equal to the du. So I have 2x plus 3 times the natural log of u plus c, or 2x plus 3 times the natural log of x minus 2 plus c. So by doing the division step, I was able to simplify into one really easy integral and then one that came out really well with that u substitution. Again, letting u be the denominator. Let's try one more like that to finish out this section. So I definitely see a numerator that's got a degree that's higher than the denominator, which is always going to suggest long division as a strategy. So let's try that. I want to divide x squared plus 4 into, and I'm going to rewrite this as minus x to the 4th plus 6. Negative x to the 4th divided by x squared would be minus x squared. Multiplying would give me negative x to the 4th plus, or excuse me, minus 4x squared. I do want to subtract, so I'll change both of those signs. And that's going to bring down this 4x squared, and that plus 6. Divide again. 4x squared divided by x squared would be positive 4. And then multiplying, 4x squared plus 16. And I'll subtract those, giving me a remainder of negative 10. So I'm going to go ahead and rewrite my integral as the quotient minus x squared plus 4 plus the remainder, negative 10 over x squared plus 4. All right, so let's see here. I would have the integral of negative x squared, that's an easy one, negative 1/3 x cubed. And the integral of 4 would be 4x. And I'm going to pull the minus 10 out. And then what I have left is the integral of 1 over x squared plus 4 dx. All right, let's go ahead and try our usual little trick here, letting u be the denominator. So du dx would be 2x. Du is 2x dx. And 1/2 du is equal to x dx. All right, so for the first time, my u substitution has failed me here. I definitely have a u in the bottom, but notice what I don't have. I don't have an x dx here, right? I can't manufacture an x. I can't make up an x where I don't have one. And so since I don't have x dx, I just have 1 dx. This u substitution isn't going to work. In fact, with what we know right now, we actually can't do that integral. We're going to find in the next section that there is a way, but we haven't studied it yet. So I'm going to leave it right there and say, I think we need a little bit more before we're quite ready to do that last integral. But the u substitution itself, I tried it. I didn't have what I needed to replace the dx factor, and so I simply can't do it that way. All right, that brings us to the end of topic F. We will go on to topic G next time.